Okay, let us begin our discussion. This is a third lecture. Let us first try to revise what we have done in our last week, just in order to bring some continuity in the discussion. Okay, so last week when we begin our discussion, we first discussed what is the mechanism of molecular evolution and how it led to the foundation of the field of sequence analysis. Okay, then I introduced you with the concept of pairwise sequence alignment. Okay, and in a pairwise sequence alignment I introduced with the concept of what is optimal alignment. Okay, and you can align the two sequence by either global alignment, or you can align the two sequence locally by local alignment. And we have also discussed what is global alignment, what is local alignment, what is the difference between global alignment and local alignment. Okay, then we started with how many methods are there by which you can perform this pairwise sequence alignment. Okay, we discussed in detail about this dot matrix method or dot matrix analysis. Okay, and what are the advantages of using this dot matrix analysis, what are the disadvantages of using this dot matrix analysis. Okay, and we also started discussing what is dynamic programming, right? And I gave you what is the concept of dynamic programming, and I introduce you with what happens in a typical dynamic programming approach, or in a typical dynamic programming protocol, if you follow uh, to align the two sequences as such. So what can you expect? Okay, I told you that you would have to first create a comparison matrix, then you need to transform that comparison matrix, then you need to perform that you need to perform a traceback of that transformation matrix, and finally you can obtain the final alignment where you can decide where to give gap or not. Okay, so like in our previous lecture, uh, I have shown you a kind of simple scoring scheme where we gave the score of 1 wherever there is match, and a score of 0 wherever there is a mismatch. Okay, so that was this is a very hypothetical example, and we cannot proceed with such a simple scheme. Okay, because it appears to be quite binary. Okay, that is, you would score in the sense ki if there is identity, then and then we will give the score of 1. Otherwise we will directly give the score of 0 if you found that it is not identical. Okay, so what you are doing over here is that you are considering only the identity between the two residues of either nucleotide or protein sequences, if you are trying to compare the two sequences as such. Okay, but my friends, biological system on the other hand are not always binary. Okay, uh, we cannot take account of similarity in such schemes if we use the same scoring scheme. Okay, so well, say for example, if you are trying to align two proteins, then proteins are known to have structurally and physicochemically similar amino acid residues. Well, say for example, one of your protein sequence might contain aspartate and another sequence might contain the glutamate at the same position. And now you know that this aspartate and glutamate, both being negatively charged amino acid residue, they can be paired. Okay, in the similar way you might end up having a lysine at one sequence, and you are trying to align that lysine with rg9, we'll say for example, in another in the next sequence in pairwise alignment. These two are positively charged amino acid residue. Okay, and such replacement or such pairing is also possible in biological world, right? So if you stick on to very simple approaches like this, then you might end up missing some important features of biological world like similarity as well. Okay, so my point is that such similarity would be missed if you rely on such simple scoring schemes. Okay, so let us today learn some real life scoring schemes and scoring matrices that are devised and used to solve real time alignment problem. Okay, so this is what the main topic of discussion would be for today's discussion. Okay, so we would be discussing more about scoring matrices. Okay, so now we'll say this scoring in an alignment. Okay, scoring in any alignment is done through a scoring matrix, as you can see over here. This is called as a scoring matrix. So whenever you try to align the two sequences, you are supposed to score them using something called as the scoring matrix. Okay, so first let us try and understand what is the scoring matrix at the very first place. So सबसे पहले so for example, let us first try to understand ki what exactly is this scoring matrix. Okay, so in reality a scoring matrix is nothing but a table of value, as you can see over here. Okay, so if it is a table of values, then the values must describe something. So whatever values you can see in this scoring matrix, they must describe they must have some significance. They must play some role, right? So what are these values now? Okay, so these values in your scoring matrix, so these values describe what might be the likelihood of a residue pair occurring in an alignment. Okay, so things would be more clear if I give you an example. So now consider that you are trying to align two protein fragments with sequence 1. This is your first protein fragment which with sequence PHQGD, and you have got another protein sequence QSTEG over here, and you are trying to align these two protein sequence. Okay, then as per our previous lecture, if you are trying to align these two protein sequences using dynamic programming, what is the first step that is needed to be done? We would need to create a comparison matrix. Okay, so you would first try to create a comparison matrix out of these two protein sequence that you are interested to align. Okay, now in order to fill up this comparison matrix, you usually refer to scoring matrix. Okay, in order to fill up the comparison matrix, you would refer some scoring matrix, say some standard scoring matrix. Okay, so this is what things would happen. Now when you create a comparison matrix and now you want to populate this comparison matrix with say some values, and these values are supposed to be inferred from the scoring matrix. So this table is to be referred in order to prepare your comparison matrix while aligning the two sequences using dynamic programming approach. Okay, so how do we do that? Well, the procedure is quite simple. In whatever scoring matrix, empty scoring matrix that you have generated, each and every position or box would represent the alignment of one residue with another residue. Okay, so this box represent the alignment of P with Q. Okay, now in order to fill this box in your comparison matrix, you would refer your scoring matrix. Okay, now what is the likelihood of aligning P with Q in these two sequences? Now here is the value, or what we call it as the likelihood of this P getting aligned with Q in the two sequence. What is the likelihood value? The likelihood value is of 0. So we put 0 over here. Okay. Similarly, what is the likelihood of this Q getting aligned with S? The likelihood of this Q getting aligned with S is -1. Similarly, over here you can see the likelihood of this aspartate getting aligned with this glutamate is 3. You see over here, this is aspartate getting aligned with glutamate. Okay, so what is the likelihood of this glycine getting paired with another glycine in next sequence? The value is 5. Okay, glycine getting paired with glycine, the likelihood value is 5. So this is how you use the scoring matrix to populate the comparison matrix. And what do the values in this scoring matrix refer? The values in this scoring matrix refer what is the likelihood of any residue pair to occur in your alignment. Okay, so well, let us go in more details, like well, say for example, the scoring in your scoring matrix, this is what we are talking about. In your scoring matrix, the value gives the likelihood of pairing your P with Q, that is the value is 0. The likelihood of your Q getting paired with S, the likelihood value is -1. Okay, now you must remember that residues which are most likely of getting paired in your alignment are given higher values. Okay, for example, the likelihood of pairing your D with, well, say for example E, that is glutamate, is given the higher likelihood value of 3 as compared to the value of pairing D with C, which is -5. D is, well, say for example, D is negatively charged amino acid, while your C, that is cysteine, it contains a sulfhydryl group. Okay, so physicochemically, these two amino acid residues are very different. Therefore, their chances of getting paired, the likelihood of getting paired in an alignment are very low, and therefore they are given lower likelihood values. On the other hand, your glutamate is physicochemically very similar to your aspartate. Therefore, in comparison to the alignment of your glutamate with cysteine, the value of likelihood of alignment of glutamate with aspartate is high. Okay, so in other words, or in simpler words, a scoring matrix is a table of values that would describe the likelihood of residue pair that might occur in your alignment. Okay, what is the possibility of the residue pair to occur in your alignment? Okay, so now let us talk about how these values in your scoring matrices are obtained. Okay, so now the values in your scoring matrix are nothing but log of ratio of two probabilities. क्या है? These are log of ratio of two probabilities. Probability of meaningful occurrence of substitution in a residue pair by the probability of random occurrence of substitution in a residue pair. Okay, well, now the logic is simple. Okay, so this value of likelihood being a ratio of two numbers, being ratio of these two numbers, the value of this ratio will be high if the value of numerator is large as compared to the value of denominator. Okay, now in order to have value of likelihood of substitution to be high, it is necessary that value of probability of meaningful occurrence to remain high in comparison to the probability of random occurrence. Okay, then the log odd value of this log odd value that is calculated for substitution will be high, and the substitution in the two sequence would be considered as significant. Okay, now the next question might pop up in your head: from where do we calculate these probabilities? Okay, so let us first try to answer this question. Okay, so these probability values are basically calculated from the samples of actual alignment that are known to be valid. Okay, so we will revisit this point just in a while, but for time being you should be agreeing with the fact that more the positive the score, the more likely is that the substitution would be significant in your alignment. Okay, and by that I mean that whatever substitution that you are trying to compare might have evolutionary background than just might have occurred by mere chance. Okay, so this is the take home message. So more positive the score in your scoring matrix over here, okay, the more likely is that the substitution that you are considering is biologically significant. It might have some biological meaning behind it, rather than just you might end up aligning those two residues just by chance. Okay, so well, now besides besides probabilities and log odd calculation that I have shown you, well, there are several other aspects that are needed to be taken into consideration while designing such scoring matrices. Okay, for example, the residue substitution that you would consider while aligning the two sequences, these substitutions are based on the genetic code. Okay, well, say for example, suppose you have two sequences that I have shown over here: ET, and L. Okay, and their subsequent codons are shown on the top. Okay, on the top of the sequence. So now, in this case, in this particular case, okay, it would take only one mutation in a codon to bring about replacement of this aspargine to lysine. Okay, if you well, say for example, if this C is mutated by A in this codon, then the resulting amino acid residue that is coded would be replaced by from this aspargine to lysine. Okay, and therefore such replacement are most likely to happen. Okay, now if such mutation do happen, okay, if such mutational event do happen, then it must be accepted by selection pressure as well. Okay, this is an important criteria. Okay, so by that what I mean is that if mutation happens and if the protein loses its activity, okay, then such mutation will not be accepted through the process of natural selection. Okay, in contrast, now consider this next example. Okay, in case of this alanine, which is coded by the codon GCG, it is least likely that all of the three nucleotide in this codon will mutate at the same time, at the same location to AUA, and and that would result in substitution of A with I, that is isoleucine. Okay, so it is highly unlikely that all the three residues in your codon, all the three nucleotides in your codon would mutate at the same time at the same place, because mutations are random, right? So such a kind of replacement or such a kind of substitution is very less likely to happen. Okay, so all I want to demonstrate is that in nature, the substitution of one amino acid residue with another amino acid residues are affected by the genetic code of the amino acid residues as well. Okay, one more thing that you should also take into consideration is that the genetic code are also degenerate. Okay, there is degeneracy in genetic code, that is a single amino acid residues can be coded by multiple codons. Okay, well, this is just an example that I am trying to give you, right? So the take home message from this slide is that in nature, the substitution that are occurring in the two amino acid residue sequences that you are comparing, these substitution might be affected by the genetic code of amino acid residues as well. Okay, now let us move on to the next aspect. Okay, so the next aspect that is needed to be taken account while creating such comparison matrix is the physicochemical similarity between the amino acid residues that are being considered for substitution in the alignment as such. Okay, so the physical similarity of amino acid also play an important role in the substitution. Okay, well, say for example, a very conservative change of leucine to isoleucine is more likely to be accepted, it is more likely to be happening than the replacement of leucine with tryptophan. Okay, these are conservative changes. If leucine is replaced or if it is substituted by isoleucine, both of the amino acid residue have similar physicochemical property. More likely is that these substitution would be selected by nature in the process of natural selection, as compared to non-conservative substitution of leucine with that of tryptophan. Okay, why? Because it would have completely different properties, and there is possibility that your protein would lose its activity. Okay, and such a kind of mutations or substitution are not the selected further in the process of natural selection. Okay, good. So now I hope you are now comfortable with the concept of what a scoring matrix is, and what are the values that are present in your scoring matrix, and how exactly the values should be. Okay, so let us now move on with our discussion on what are the two major families of scoring matrices that are present in that are normally used while comparing the two sequences. Okay, there are lot of other scoring matrices also, but these two scoring matrices that we are going to discuss today are most common scoring matrices that are implemented in dynamic programming for aligning the two sequences. Okay, so uh, these two scoring matrices are called as PAM series of scoring matrices and BLOSUM series of scoring matrices. Okay, so we would discuss these two scoring matrices in our next video. Okay.